my screen and then I will start. All right. So let's just do one more thing on here. Okay. Okay. All right. So thank you so much for joining again. My name is Pritul, and this session is going to be about A/B testing statistics, visually explained. All right. So this is going to help a lot of you folks who run experiments already or who are in the field of CRO and already making decisions on your experiment readouts, but sometimes facing difficulty explaining some of the decisions to your stakeholders, whether to end the experiment or launch the experiment. It's also convoluted statistics that is behind it that you may not be aware of how it actually works, but it's just someone has just told you like p-values, look for low p-values and then launch, right? So I want to take this time and really go into under the hood and basically just demystify what the statistics is about and how it actually works and how it has been combined together in the recent field, or at least in high-tech field, uh, from some historical theories, and then it has been like scaled up into large platforms. So quickly, I want to go through some high-level roadmap. I don't have slides. I just have this whiteboard that I have created, or this is the mind map actually that we are gonna go through in this session. Uh, we have some disclaimer. So I'll go through the top section, webinar tools, audience. I'll go through who am I, why this session, why am I doing this, and what topics we won't be covering. And then we'll come to the more detailed stuff, which is the actual topic of today, A/B testing, and there is a several parts underneath it. And then lastly, the closing statements. If time permits, we will go through some Q&A, but uh, I don't know if we'll be able to even make this through. I don't want to stretch it all the way to 2 hour mark. It would be just too much time consuming for other folks. So I'll try to end this at 1.5 hour mark. All right, so let's begin. So first and foremost, the webinar is being recorded, but it will not be shared. If you want to rewatch it or any part of it, reach out to me and I will be happy to figure out how I can do that for you. Okay. If you have logged on phone and watching this on phone, please switch to a larger screen. I will be showing you numbers and stuff like that, so it's gonna be too hard to squint your eyes, and then it's not gonna be a good experience or learning experience for you. I am going to be tab switching in this presentation. It's a whiteboarding exercise, so I'll be switching my tab. I'll be zooming in and out. You'll hear my keyboard click a lot, my mouse clicking. So just bear with me on that part. That's just technology stuff. I just wanted to let you know about what you should expect from this whiteboard session. Oh, I'm seeing that it's lagging, it's blurry. I think some of the folks are having this issue. If it helps, I can actually turn off my camera, and that way the bandwidth can be saved and other folks can see it. So I'm just gonna turn off the camera. All right. So yeah, the next one is please do not reproduce this webinar in any form or content without my permission. If you need anything, I will be happy to share it with you, but please reach out to me. Again, the content of this event is for educational purposes only, and it does not include any specific facts of my current employee or any previous employee. Any opinions expressed are solely of mine and are based on my personal experiences and does not reflect of any of my previous employers or current employer. And lastly, you might have had to enter an email to get through the stream. Um, you will not get any emails from me because I don't want to spam anyone anyways. If any email does come through you in your inbox, then it mostly would be from this webinar company. That would be if at all it comes. I've already activated the setting where it purges the emails after some days anyway. So yeah, that's that. All right. Next one in the agenda. So as I go through these agenda items, I'll just be marking these as grayed out. So we've covered that part. Our goal is to mark everything gray. Webinar tools. On you have already figured out the chat box. So feel free to uh, chat stuff. If I see a lot of comments that saying it's too blurry or hard to see content. If this is getting worse, then I will have no other option but to share this recording later on, and I will. You will have to reach out to me though because I won't have your emails. Um, so yeah, just sorry about that. I signed up for this tool because they did say that they can host up to 5,000 participants in this, and I don't know how they are able to handle this if they are not even able to handle 300. But I'm gonna continue this. There is a recording, so just reach out to me if you need it. Yeah, webinar tools. Again, there is a chat box. I might open a poll or something in the middle when the right section comes. So yeah. So just keep an eye out for that. All right. So we've covered that. The next one is about the audience, right? So who do we have? So just about a minute before 9 a.m., I saw there are 1,448 registrations on this. So definitely overwhelmed with the support and with the response for the interest in this topic. We only have about 400 folks joining in, which is fine. I regardless expected about 20-30% conversion rates to show up conversion rate, so which is in line. And as time goes on, we'll see. So who all are in the audience? Who all signed up? So we have data analysts, data scientists, researchers, statisticians, product managers, CRO strategists. CRO, if anyone's not aware, it's conversion rate optimization. Um, Strategists and consultants, software engineers, managers, directors of analytics and data science, head of experimentation programs across different companies, and many, many, many more. We have new college grads, we have current students, we have aspiring data scientists and career opportunists who wants to switch their careers. We have folks from FANG, Fortune 100, Big Four, NASA. We have folks from analytics consulting firms like Mu Sigma, Tiger Analytics, Latent View Analytics, and many, many, many other more companies. We have folks representing from Optimizely, AB Tasty, Split, LaunchDarkly. These are some of the top vendors in the space of experimentation, who who other companies can actually integrate with their own platform and start running experimentations. I have current friends joining in. I have former colleagues. I have former classmates and also former roommate who signed up for the event. I'm not sure if any one of you joined, but thank you for signing up. Um, all right, so what's next? Yeah, so I don't have a slide on who am I, except the poster that I had posted. Um, I am a data scientist currently in Apple's experimentation science group for AMP. I was an experimentation scientist in eBay before, and I was a product analyst slash data scientist at Yahoo Search before that. I have done a lot of work on experimentation at eBay. I have uh, completely, I basically helped completely flip the experimentation platform by implementing some of the most robust statistical methods as well as tooling in place. And all of that actually came about by learning from this field. Um, I was an outsider to the experimentation space, as a lot of us are, anyways. I took a lot of statistics courses throughout my academics, like at least 3 courses that I can remember. But I could not understand what is all this about. What is experimentation design? How do you compare the results? Things like that. Like all the null hypothesis and alternate hypothesis and power, all you would confuse me until I was offered a job at eBay where I had to be now part of the program, which is going to be experimentation platform, and it's a core platform, central platform where you make the platform so useful that the product managers can um, uh, basically test their ideas and do good readouts. So that actually sent me on a journey to learn these whole concepts again and understand it in the way that I can actually teach to anyone, right? It's like basically explain like I'm five, kind of a version, but this may not be that rudimentary. I'm just trying. I'm still going to try my best to explain it as in as easy fashion as possible. Again, I think I covered some of this. Why this session basically I myself had difficulty grasping this stuff, and there is another angle to it, which is I was told by a few of my colleagues that I do this job of explaining things very well at eBay. So why not just expand and start talking to larger forums, and maybe they will benefit from this. So I've been snoozing on that for like almost 3 years. I have not taken any action. Last year, I was also reached out by another former colleague to actually make a formal course out of this material, but I snoozed on that as well. But this year, I wanted to push myself and see what I can do with this. So when I started this event on LinkedIn, I was only expecting about 25 to 30 people to actually sign up, honestly. And at max, it would stretch to like 50. But it blew up so much, like in few days I had like more than 500 sign up. So now the stakes have gotten really, really high. And yeah, I mean, the more the merrier. So I hope this I'm going to make this time worthwhile for you as much as possible. And yeah, hope you have some learning out of this. I'm just going through some of the uh, comments again. There is still a lot of folks who are saying, can I do this on Zoom? I cannot do this on Zoom because it has a limitation to host only 500 people. I do see that right now we have 400 folks. I'm not sure if any more people will be joining later. Um, if I see, since a lot of you have this issue, reach out to me on LinkedIn. Uh, since you've not been able to see this, I will be happy to share a private recording to you. All right. uh, all right. So this is done. And what are we not going to discuss? Let's see. So I won't go into details of experiment designs, like what are good designs. I won't go into experimentation platforms. What are the basically features of what should be good features of experimentation platform to prevent false positive, false negative readouts, things like that. I won't go into Bayesian statistics, no sequential testing, no non-parametric methods. I won't be talking about metrics or KPI selections. I won't be going through any complex formulas on calculating stuff. And I won't be even talking about any modern causal inference models that basically help you measure incrementality stuff. None of that. This is purely going to be about basic statistics, which has been highly misunderstood and being still used in a lot of experimentation platforms, which causes a lot of folks to make erroneous readouts. So, all right, so we covered the top section. Now let's get into the meat of the session. So A/B testing statistics. First and foremost is the topic of unlearning. We have a varied group of folks in this session, right? I want you to first unlearn everything about your statistics knowledge that you have. Unlearn what p-value means to you. Unlearn what hypothesis testing is. Forget about that. You have to reject null hypothesis when p is less than 0, um, because there may be some of you that uh, may not have enough understanding of how these things work together. And if you don't have this understanding, you might have some superficial knowledge. I want you to unlearn that and rebuild this from ground up. And I will walk you through how you rebuild this knowledge from ground up. Uh, this is a meme that I found from the great philosopher, intergalactic of intergalactic world. You must unlearn what you have learned, otherwise you cannot make progress, right? So yeah, that is my message to you for now. There are statisticians who would absolutely know all of this stuff, um, but there are other folks in this forum who will not know all of this. So, or who may know things, but they want to grasp it from conceptual perspective, or conceptually, basically. So that's about unlearning. Let's get that out of the way. All right, first A/B test. So let me go through that. The first scientific um, account that you would say that has been known to science world is, what was the first control experiment? It was by James Lind, who was a surgeon on British Navy, and he did this first control experiment on 20th of May. This should be not 1947. This is 1747. Um, to identify the cause of scurvy on board the ship called Salisbury. Now, what is scurvy? Scurvy is a disease that where gums are actually sore, and then the teeth fall out, and then people die from it, from the wounds. So it was a serious disease where Navy kept losing soldiers to scurvy throughout their journeys, and at that time the ships were very slow, so the sailors had to be out for several months or years even on the sea, and they would absolutely lose a lot of sailors to scurvy. So what did James Lind do? He picked up sample size of 12 patients who had this scurvy disease and who had very similar intake of food every day on day-to-day basis, who lived in the same section, which was like a cordon of area of like where patients should stay. And so basically he controlled for a lot of variables, and he ensured that all of these 12 patients are almost similar to each other, and they won't be affected by any other factor other than what he's going to introduce to them. What did he introduce? So he did actually A, B, C, D, E, F, G, uh, or EF version of it straight up. So he took he gave two people quarts of cider. He gave two others a mixture of sulfuric acid and alcohol. He gave two others spoonful of vinegar, and two others seawater, and two of them two oranges and one lemon, and then two of them bigness of a nutmeg. I don't even know what bigness is, but it was something about nutmeg, and there was some crazy concoction of nutmeg. Um, and he observed the folks with, and he when what his observation was that folks with two oranges and one lemon each every day, the two guys who ate that, they actually recovered. And by the way, they had run out of oranges and lemon by the end of sixth day. They could only spare as much as they can, and they gave it to them. And but 6 days were enough to 6 days of consumption was enough for these soldiers to actually recover. These were the only soldiers that fully recovered, like within next few weeks. So he published his work like after 7-8 years, but it wasn't accepted by the British Navy and make like oranges and lemon like a mandatory on ship. It didn't happen right away. And then throughout time, you would see on in history, if you go online and read about this, there have been back and forth where scientific community said, okay, oranges and lemon does not work, but sometime it says, okay, it does work. But then as time progressed, there were more and more data collection methods. There were more and more inventions that came out, and not until like in 1950s they realized the real reason for scurvy was lack of vitamin C. It was not until 1950s or something they couldn't they identified vitamins. So that is when the real reason was identified. But until then, there was a lot of back and forth between this theory and yeah, but this was the first known control experiment. How does this A/B testing work in modern world, right? So it is being used obviously in medical research, uh, drug development, psychology, and a lot of other fields in medicine, and mental health. On online testing also, it's being used very widely, where it's this whole method has been easy to scale up. um, just about yesterday, I saw this for Google, right? Two exact same queries, Stranger Things, but Google is testing this central carousal for top stories. So on in one of the experiences, it is testing a three story with a carousel. You see this button that you could click, and it goes up to 10 stories. And this other version is only four stories. These are in this layout, and there is no carousel. And they would measure this, right? Whatever their key metrics is that they want to um, move towards. I don't even know which one is test and which one is control. Um, so I really don't have any idea. But this is how it is possible. There are so many other orthogonal experiments that could be running in here. I don't even have any clue. But in online world, the platforms have evolved so much that you could run tens of thousands of experiments at the same time to millions of users, and you can get concurrent readouts throughout your site and make a decision, right? So that is the modern setup of these experiments. And it all started with a basic world of p-values and hypothesis testing, the way it works in medical field. But then especially in high tech world, this has been now evolved into more advanced methods like Bayesian statistics or sequential statistics and things of that nature, or causal models even. So so but we won't be talking any of those detailed stuff. I want you to understand where this thing comes from, like what is the basic statistics behind it. So then after that, you can go and chase all the other advanced statistics by identifying the pros and cons of this current method. All right, so going back, so yeah, so that is the modern online control version of experiments. Now let's go through the visual exercise. I'm just gonna quickly see any comments. I think it's fine. We have still 400 people on here. All right, so let's go through a visual exercise. Um, I have here three different charts that are hidden. Think about that experiment that you just saw for Google. And what I'm gonna do is this is a chart. This is a metric value on y-axis and time on x-axis. So I've covered the chart deliberately, and I want to simulate how things actually work in our online world. Right? Historically, the tests were developed. Basically, you didn't have real-time data, right? But technology had made it possible where you can see real-time data and make inferences. So I want to just simulate that environment to you, and think which line between this test or control is the winner. Okay, try to guess which one is the winner. So I'm gonna start, and please type your comments in the chat box, whichever you think is the winner. Right, as time is progressing, you get this data, and this is how both of these lines are going forward. The teal is the control, the purple is the test, and you're getting more and more data coming in, right? Are you able to predict which line is the winner right now? Um, I'll continue with more. I'm sure there is some lag, so I'll wait for the responses. So it continues going on, continues, right? You keep going on, you collect more data. Are you able to still predict? Likely no. All right. So keep going on, and maybe you are able to predict. I don't know, right? It's very hard for me to tell which one is the winner. All right. So this is the first one. Um, Now I'm going to move to the second example, same one, but this time pay more closer attention. And I see some folks writing control, unable to predict, test, control. So it's all right. It's perfect. Um, it's going to be a mixed bag, right? It was a hard one. This one may be a little bit easy. So as time goes on, the data is coming in, we are able to collect more and more, and we are able to see. Are you able to say for definitely which one is the winner in this one? Most likely for me, I would say, okay, the purple is the winner over the teal one, or the control, right? So test is a winner. um, I'll keep going. I'll take this forward even more. Now I have a little bit more doubt over here because it kind of dropped, but this teal line has gone up, but then it came back and won again. So overall, maybe I'm thinking the purple did win, but again, not too sure. I did have some high hopes initially, but then again, it's hard to tell which one is the winner. Um, All right, so I'm just gonna move to the last one over here, which is gonna be, now you can tell me which one is the winner, right? Are you able to tell which one is the winner, right? You can, I can tell it's the purple one clearly. As time goes on, I can still tell it's purple. It's still purple, purple, right? It's test bucket. That's a clear winner. So it's one, right? Um, so All right. So out of these three, I just want you to now internalize, go into your subconscious and see what algorithm did you use to predict which one among this is the winner, right? Especially for this third one. The first two are definitely a bit harder to tell, but what algorithm did you use? Either you used your subconscious part of identifying a white space in between these two lines, and the more the white space, you can separate these two lines out and say, okay, this is a winner. Um, the other way you could have done is use a little bit of more conscious effort and try to rationalize, okay, I have my peaks and troughs for both of these lines, and they both are at clearly different level on y-axis. So, and as I see these peaks go up and up, I am able to uh, define a fine line somewhere around here for this purple metric, right? I'm just going to put a line somewhere over here. um, Oops. So this one is the line. I don't know why this is getting stuck. Let's try again. So somewhere over here, and we'll just change the color to purple so you can see. So maybe this is the line for this, and maybe this is the line somewhere here for this, and you can see there is a clear separation on these two lines, and say that this is the purple is clearly the winner, right? Now hold that thought. This is something very similar that happens in statistics, although statistics is based on math, and math is able to separate out even these first and second cases really well. This is just by, if you just do like an average of this, of each two line, you can tell which one is the winner and which one is the loser. But there is more to it than that, and which brings me to my next topic, of actual how did this um, how did we come up to using p-values and hypothesis testing in A/B tests world? All right. So let's start with Fisher's significance testing. Now, here is where statisticians would have a lot of knowledge already who are already attending here. So it's going to be a cakewalk. But for some other folks, it's definitely going to be a little bit more effort on understanding this. So please pay attention and take notes if you have to. So Fisher's significance testing. It was popularized by Ronald Fisher, who was a statistician in England. Mainly, p-values were not created by Ronald Fisher. It was created by Carl Pearson, the person who invented the chi-square test. But they were not as popular. But Fisher made them more popular by basically showing how to actually apply to a wide variety of situations. So, what is Fisher's significance testing, right? So Fisher said we have a null hypothesis, and I'll talk to you what null hypothesis means. But basically, we have a null hypothesis, and what p-values are going to measure is what is the um, what is the probability of observing something in the face of null hypothesis being true, right? So that's just a high level thing. I want to actually take a quiz on you, but I already probably gave out the answer. so so a lot of folks, when they say p-value is less than equal to 5, they have no idea what actually it means, right? Either you are confused whether it's a type 1 error or is it an actual effect are we talking about, or what, right? And let's just Google, right? Google says p-value is the probability that and then all of these are showing up over here. All right, p-value is the probability that null hypothesis is true, blah 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 blah, right? All of this shows up. I want to actually add a poll here, just so that um, you can answer me what the p-value. What do you think p-value is the probability? So I'm just starting a poll. I'll give like about 20-30 seconds for you to answer, and yeah, all right. So the poll is on. Feel free to answer. What do you think the p-value is? And we'll see what the results look like. I'll end the poll in 15 seconds. All right, I am ending the poll. So amazing. The results is 59% of the folks said observing an effect equal to or extreme given the null hypothesis is true, which is right. And yes, this was going to happen because most of the data statisticians know the correct answer to this. But this lecture is specifically going to help understanding for the 9 folks who answered all the other answers, right? 19% going to null hypothesis being true, which is what Google says as the number one result, or at least in the suggestions. And the third one being rejecting null hypothesis and committing type 1 error. So the correct answer is the majority of them. So congrats, all of those who got it right. I think I already talked about it anyways before I even entered the poll. So yeah, let's get back to the board. All right, so yes, this is problematic definitions that show up everywhere, which are the p-value that the null hypothesis is true, this one, the probability of type 1 error, this one, these are all incorrect. And none of these are actually correct. The correct one was the one that I actually showed. Let me see what Wikipedia says, right? The Wikipedia is saying null hypothesis significance testing, the probability of obtaining test results at least as extreme as the results actually observed under the assumption that null hypothesis is correct. I want to deconstruct this for folks who did not understand or how to explain this well. So this second part, under the assumption that null hypothesis is correct. So it is already given that the null hypothesis is true. It doesn't matter whether you think it's true or not. It's already, the assumption is true that null hypothesis is true. Now, what you have observed in real life, your observed data, what is the probability of that happening under the assumption that the null hypothesis is true? If it's less and you actually observed it, that means that can be either one of the two things, right? Either your observation is like very rare, or your null hypothesis is actually incorrect. One of the two. So your observation being very rare, that's why we aim for p-value less than um, uh, equal to, like, we want it to be so low that null hypothesis can be rejected. Like, we don't want the null hypothesis to be true. I'll give examples for this. Um, think about this, right? We have about 416 people in this live webinar. If I were to ask, what is the probability that at least two people has the same birthday? So it doesn't matter the day or the date. Sorry, not, it doesn't matter about the year, but the day and the month has to be the same, right? If you think logically, you would know that there are 366 days in a year in a leap year, considering right now we have 411, which is higher than the number of days. So there are at least two people with the same birthdays on this specific forum. Now, if I were to ask, what if I randomly picked two people out of this thread and asked, do you have the same birthday? What is the chance of that happening? I want to start a poll on this, and you can answer that. So if I randomly pick two people, you should see the poll on your screen. What is the chance that they have the same birthday, right? I'll end the poll in 15 seconds. All right, I'm ending the poll. So yeah, the most answers, no, most votes went to almost no chance. The next one 50-50, and the third one is very high chance. The almost no chance seems about right, because our subconscious mind kind of knows how to evaluate these probabilities when it comes to like the scenarios in which you are exposed more often to, right? Randomly pick you two people, but then there are 365 or 66 days. How can they have like same birthday? It's very rare chance, right? But it's close to zero. There is still a small chance, but it is almost close to zero. The other way could be if I pick two people, and or if I just said that this is their birthday, let's say January 16th today, uh, there are at least two people on this forum who has a birthday today, right? Again, very low chance of that happening. Although if it is, happy birthday to you, and thank you for attending this on your birthday. But otherwise, you're right. So some of these probabilities work very well in our head. The other example that I can give is, let's say in your head, so let's talk about null hypothesis before that, right? What is this null hypothesis? I'm going back and let's talk about this null hypothesis. Oops, where is this? This null hypothesis over here. What is the null hypothesis? Null hypothesis is basically your the way I understand it, or the way I keep myself uh, with the definition is like this, right? I'm just gonna, so null uh, null hypothesis is let me just reduce, is my current understanding of the world. All right, so what does this mean? What does this mean really? Null hypothesis, my current understanding of the world, right? What it actually means, what I'm saying is, what is the current understanding of you for this world, right? So in the example of birthday, your current understanding you had was there is very there is some kind of a distribution that is available in this world, and you know that there is very rare chance that two people can have a same birthday in a random forum, right? It's less, although I mean, two people will have the same birthday, but which two specific people you don't know, right? You have that kind of a general understanding. So, but if I were to pick two people and ask them, and they did have the same birthday, then my current understanding of the world is untrue, um, or at least for this record, this specific instant, it is not true. The other way of putting this is, let's say I and my wife, we normally just text each other during the work day time, and if I have a meeting, we just never call each other, right? Or I may never pick up the phone or whatever, right? But the general understanding is we first text and not call, unless it's a super emergency. Now, most of the days go by that, and that is my understanding of the world. That is my null hypothesis, that my wife is gonna text me instead of calling me. But one day I'm in a meeting and then I get two or three back-to-back calls and I'm unable to pick up, right? But now suddenly my current understanding of the world, which was that he's not going to text me, he's just going to call me, has changed, because now I know that there is an emergency. And our subconscious mind, right, it goes through such null hypothesis rejections on everyday basis. We don't even realize this, that we are doing this, but this is how we make decisions. This is how we move forward in our own lives. There are so in my case, in my wife's and my case, this was basically an emergency call, meaning an extremely rare event that happened, and maybe it's an emergency, and I need to absolutely pick the phone up. So. Uh, so yeah, so that is what the null hypothesis actually was invented as, and the p values are basically nothing but the probability of an event happening. Let's take another example. Now this time we'll put more numbers, because this is not your daily, like your subconscious mind does not know what's happening when it comes to rainfall in Hawaii, right? For example, let's say I want to go to Hawaii and I'm planning, and I read somewhere that, okay, this year the average rainfall in Hawaii has already been like significantly higher. Like it has been really, really wet conditions in Hawaii, and it has not been a normal year. Now, for me, I cannot hold this world of null hypothesis, which is my current understanding, in my head for Hawaii rainfall, right? Because it's not something that I look at every day. This is something that is new to me, and I'm gonna have to pull some data for this. So, being a data scientist, I download some data, and I get a data from 1920 to 2012, like about 93 years of data, and I get annual rainfall in inches. And then I have this line chart that shows up, and you see the fluctuations, right, happening throughout the time period. Now, let's say someone tells me that okay, it's gonna be probably about 100 inches at least this year, and that is my basic understanding. All right, so now my null hypothesis is, I need to form my null hypothesis first of all. Like, what is my current understanding? Because I don't even have the data. So let's form that null hypothesis. Now, what you do, you have this data. How do you form? Like, you can compute the average of this data set, right? If I just do that and I computed average, I get 68 inches as an average for this data, right? Data scientists, what they do, or statisticians, they'll just create a, a frequency distribution chart, which is a histogram for this, which is much easier to actually process and read. So so folks who are not doing this on daily basis, right? The way this works is we just take this records, we disassociate the year column, right? So for example, assume that there is no year column, and we just create a bar chart on this, wherein what we are trying to do is we take each of these projections that you have on the line and put it on this horizontal axis, or sorry, vertical axis, like project it on the vertical axis. If two of them stack with each other, it's fine, it's perfectly fine. So that is what frequency distribution chart is about. And you see most of the values are somewhere in the middle over here, and then there are some extremes at the top and the bottom. So the way this will look like is um, like this, right? But before that, let me restore my number of years because I need that data set. um, all right, so now I'm going to plot that again. All right, so this is my um, histogram for the for this data set. What it's telling me is it has just plotted all the different stuff on here, and I can change some settings. So let me do like 8 over here and see how this one looks. Well, this looks something like this, and let's try something else. Oops. This was yeah. So this is kind of how this data set looks, where most of the data points are between 63 and 71 inches, and you can see there is a very less number of data points on that line that were extreme on the end. After 95, it's just almost like 2 or 3 data points that went into hundreds. So if this year was going to be abnormally wet, that means it has got to be, and someone told me that it's going to be 100, then I see that 100 is, yes, it's rare, so probability of this happening is very rare. So my understanding of null hypothesis was, okay, the average rainfall is somewhere around 68, which I got by this chart, and this year it's already at 100, and which is a rare event. So but I'm observing this rare event. I know of the fact that the rare event has happened, which means for this year, I will reject the null hypothesis of the average rainfall being 68, right? So that is that is what the null hypothesis and Fisher's p-value means. Going back here, right? One thing that I want to again emphasize is Fisher only proposed about null hypothesis. Fisher did not say anything about alternate hypothesis. So the p-values only work for rejecting the null hypothesis. That's it. Nothing further than that. I got a question. Would you say this is normally distributed? Well, almost. If you remove the outliers, it is almost the normal distribution. But again, that's not going to be the topic, and we'll cover a little bit of this in later section for central limit theorem. We covered Hawaii rainfall right now. So another definition for significance test or Fisher's p-value test, right? So a A simpler example was like Wikipedia also says that significance test is like a criminal trial in which the defendant's guilt is assessed against a null hypothesis, where the defendant is assumed innocent until proven guilty. So basically, the null hypothesis is that the defendant is innocent until you have an evidence that proves them guilty, right? Now, so why did we go with the null hypothesis? Because that was the best data point that we have, and we don't want to prove someone guilty. So let's take again another example and put a criminal on trial, a cat. All right, so you come to your home and you have a cat, let's say, and you see this scene. The blinds have been destroyed by this cat, right? You put this cat on a criminal trial. Your null hypothesis is the cat is innocent. All right. Now you start gathering data of for figuring out under what scenarios this cat is going to be innocent. Maybe you have a kid who hid the cat behind the blinds, and cat was trying to escape the blinds, and in that process they mangle the whole blinds. You might think, okay, can it be possible? Well, the child, first of all, you may not have a kid, so that scenario goes off the window. Your kid might be at school, so that scenario also goes off the window. Maybe you have another cat who actually did this, or another pet who did this, but then this cat got framed in the crime, right? What are the probability of that happening? Maybe you think, okay, this is not that is not possible because you don't have another pet, or the other pet was just outside the whole time, right? You saw it in your camera maybe, and you rule that hypothesis out. Maybe someone else framed the cat, right? Who knows? Maybe your neighbor framed the cat. But again, what is the probability of that happening, that your neighbor came in the house, broke into your house and framed the cat because your cat maybe was leaving dirt behind in their backyard? Who knows? But anyways, that is, and again, a rare probability. So as you compute these probabilities, there is a very rare event that where your probability keeps on declining and declining, where the null hypothesis, the null hypothesis kind of world is becoming less and less possible. So what you're saying, that this is a rare event where the cat actually did commit the crime of destructing the blinds. And you might know from another data point, which is most of the times your cat is just fine, is just minding his own business, sleeping, whatever. But there are some rare occasions where sometimes they just destroy things, and that is what you have to kind of agree with and say, okay, in this instance, again, the cat is guilty of the crime, and you reject the null hypothesis and then punish the cat, whatever. So so that is a high level kind of examples of what null hypothesis means and what p-value means. So p-value, again, I'm repeating, p-values were created by Fisher, or not created by Fisher, but were popularized by Fisher to basically test the null hypothesis. And null hypothesis is basically so the definition of p-value basically is what is the probability of an event that you have observed would be equal to or as extreme in an outcome given the null hypothesis is true. All right, so it is a convoluted explanation, and Wikipedia does say that the precise meaning of p-value is hard to grasp, and that is why the misuse is widespread. So again, keep this in mind. P-value is obviously hard concept to explain, but most of the times you can give some examples of some extreme conditions happening. It was only meant to reject the null hypothesis. There is no alternate hypothesis to accept. Then came these two guys, Neyman and Pearson. Now, this Pearson is a different Pearson than Carl Pearson, who invented p-values. This Pearson is son of Carl Pearson, Egon Pearson, his name. So Neyman and Pearson, about the same time when Fisher came up with p-value theory, but was hard to grasp by science community. Neyman and Pearson came up with the hypothesis testing theory. All right, in which they introduce first and foremost the alternate hypothesis. This is one of the biggest differences from p-value of significance testing. So Neyman Pearson said that there has to be one alternate hypothesis if you are rejecting a null hypothesis. Otherwise, there is no point in doing this exercise, right? So that was their argument. Furthermore, their philosophy was to not reject the null hypothesis on the basis of a p-value. Rather, their philosophy was we establish we establish a boundary, a decision boundary that will help us govern our decision making uh, in the long run, right? Okay, so what I'm saying is Fisher's test works for one single hypothesis that is in question at the moment, right? And all the examples that I gave were at the moment examples. But Neyman Pearson is not short sighted. They are looking farther out and they are thinking, what if I have to do this again and again? And I keep making mistakes in my assumptions. So that is why we come up with a decisioning boundary, which are basically type 1 and type 2 error acceptance rates. And when we decide these rates, all our decision making will happen under this decisioning boundary, and over long term we'll end up making good decisions. So maybe we make a wrong decision in this exam in one of the cases, but over long run, like 10,000 or 1,000 experiments, we will end up making way better decisions than the null hypothesis than we would have in absence of this. The other thing that they added is in alternate hypothesis, you have to absolutely specify an effect size that you want to measure in the experiment. What is an effect size? For example, alternate hypothesis would say, I want to at least measure in the Hawaii rainfall example, I want to at least measure, let's say, 110-inch of rainfall, right? So that's like alternate hypothesis. You are bounding it by a condition, and you have an effect in mind. So average is 68, but I want to observe 110. So you are stating an effect size, and all of these things combine, the effect size and these error rates, alpha and beta, will help you basically come up to a decision on every trial, on every experiment, and over long run it's gonna work out well for you. The simple explanation for type 1 and type 2 errors, I'll go back to these boards, to these charts, right? Let's take this one specifically. What is the so let's say you ran some numbers, right? Now just by guessing, you said it looks like the purple line is the winner, the test is the winner, so I am going to declare that as a winner. You're not doing any statistics right now. This is just by observation. So you declare test as a winner and the control as the loser, right? So in this case, the alternate hypothesis is basically your test is a winner. And but what if there was a chance where you did end up making wrong decision, right? You incorrectly declared test the winner. So that is the first error rate, the type 1 error rate, where you incorrectly rejected the null hypothesis. So you incorrectly declared test the winner, but you didn't know, right? At least at that time you didn't know. So that is the type 1 error. And the other error could be, what if you declared control the winner, right? From this example, what if you declared control the winner, which means you fail to reject the null hypothesis, which means the null hypothesis holds true. There is nothing that you observed in the experiment, and you said, okay, control is still the current condition, and there is nothing else to declare winner. So if so, that is, and if that was false, if indeed test was the winner, but you declared control the winner, that is your type 2 error, which is the false negative rate. So if you declare treatment as a winner, that's your type 1 error. If you declare control as a winner, that could be type 2 error, but that is dependent on whether the effect exists or not. So that's how I want to explain this. We'll see further examples of how to read about this. But so let me just go back to this section again here. Yeah, I again want to emphasize this particular point. Well, this one right here. So this is what Neyman Pearson said about the decisioning boundary, right? We, without hoping to know whether each separate hypothesis is true or false, which means whether having to reject null hypothesis each time, without having to correctly know we're doing this each time, we will search for the rules to govern our behavior with regard to them. And then in the long run of this experience, we will not often be wrong. All right. So this is what they are trying to say. And this has got nothing to do with p-values, by the way. Their theory was completely independent of p-values. What they are saying is, if you are deciding an effect size, which is you want to observe 110 inches of rain in Hawaii, and this time you did observe, but maybe you incorrectly observe over long run, and you thought that you're going to reject the entire Hawaii rainfall model, which is the null hypothesis. So you may be wrong in most in current state, but over long run you will be right in doing the same exercise again and again. So these are the two different philosophies of A/B testing, that or statistical theories that have been combined in the research world currently, and a lot of time they get misused because they and the reason being the p-value threshold that is being selected. So Fisher never said p-value of 0.05 is a strict limit. Fisher actually prescribed even stricter limits of 0.02 in a lot of cases. But he said if you are putting the boundary at 0.05, you will not often be wrong. Again, his idea was also similar. You will not make incorrect. You will not falsely reject null hypothesis. So that's what he said about p-value selection. It is still up to you to decide what your boundary should be depending on your business case. And Neyman Pearson established boundaries for alpha and beta, in which they said alpha about 0.05, but again they were never adhering to that alpha level of 0.05. They said it's completely up to you to decide how you are launching your experiments. And beta of 0.2, beta is the 1 minus the power. Basically 1 minus beta is the power. So beta is generally established at 20%. So 1 minus beta is 80%, which is the power of the experiment. Now I will explain power in a little bit through some visualization, but this is what it means. So yeah, so the confusion arises between this alpha threshold and the p-value being exactly almost about the same, which is 0.05, and as a result, in a particular experiment, we wait for p-values to be significant, and then when it becomes significant, we declare one of the other as a winner. However, uh, so when we do that, we are combining two theories. P-value is only meant to reject null hypothesis. It wasn't meant to accept alternate hypothesis. And Neymar-Pearson's hypothesis testing was meant to accept alternate hypothesis if you observed the effect size of at least what you declared in the beginning, and you have met the sample size requirements, both. So when you have these both the conditions, that is when you declare your treatment as a winner, if you observe that effect. So these were two independent things, but now have been combined in our current experimentation framework, largely in almost all the fields. These things are never taken by themselves. These two are always combined going forward. But because and the very first time that I observed a disconnect between these two is when I learned about how to calculate sample size. So when I was calculating sample size through some formulas and I put all of these values in, alpha, beta, effect size, I get some number, but then that number has no association with p-value. The p-value happens independently. So p-value is a post hoc readout that happens after you run the experiment. But these alpha, beta thresholds and effect size, you are declaring before you start the experiment, and sample size before you do the sample size, before you start the experiment. So one is pre, one is post. And as a result, there is a lot of confusion when how to do these readouts. So all right, so what do I want to cover next? I want to show you how these how the power, what is the power actually of the experiment or of the readout. For that, I'm going to take this third chart, and I have something created, so excuse me for moving around too much. I want to bring these um, to normal distribution curves here, and I'm gonna take this chart over here, uh, make it larger, right? And I'm gonna flip this vertically just so that you can get some understanding of what is actually happening, right? So remember how this is the same distribution as what I had. Oops. This is the same distribution that I had um, like before for Hawaii rainfall, this kind of distribution. So when you plot this teal line, the blue line vertically on y-axis, so horizontally on y-axis, you'll get this kind of a distribution. Okay. Now let me actually shrink this a little bit so that I can accommodate the other line. So this is how it might look when you project, right, for this teal line. Now what is this is the line for, this is the normal distribution for control, where you have decided your boundary of alpha equal to 0.05. Okay, on one side, consider this example right now for simplicity. This is your boundary where about 5% of your readouts might fall, right? Not always, but this is where the 5% boundaries. Let me shrink it a little bit more. I can always zoom in. Now you have your treatment uh, data, right? Which is this one. And let me scale this back a little bit. And generally these two should overlap, honestly. Yeah, something like this. So initially when you, and this might be somewhere around here, all right? This is the middle line is the mean of this, which is the same as continuation of that line that you see. And this is the continuation of this line. Let me see if I can change this color. So make it more consistent. So, all right. So I have this color, right? Same color, same line, same two colors. Now, when we start the experiment, right? Forget about these two lines. When we are starting the experiment, and this is our null hypothesis, basically, both the means are overlapping each other. There is no difference between the means in an experiment. This is our world of, this is our view of the current world, where my mean is same as mean of control is same as treatment, and this is how it looks. As we start collecting data, and let's say treatment does have a higher conversion rate or whatever, right, higher metric than the control, this curve starts drifting away from control towards the right. All right, as we get more and more data, this can possibly go higher and higher if there is a real effect available. Now let's say this we collected all the data and we reached this point, right, which is this same line that I have here, and we reached here. So the decisioning boundary right now is this, compared to control, this is my alpha level, and I'm still under my alpha level for them for this line, which means it's not actually a winner, or actually we fail to reject the winner. Why? Because I wanted to measure at least, let's say, 10% lift, for example, and that 10% lift only happens after I cross this boundary. So I did not observe 10% lift, and this one stopped here, maybe at, let's say, 6% or 7%, and stopped here at the end of the experiment. I cannot reject my null hypothesis, and this is what it is. The power doesn't matter because this is not a winner anyways. Now, let's say you let the experiment run further and further. Now, I'm not gonna expand these lines out, but I just want to simulate that, let's say this thing moved up right over here, right? And as a result, this one also moves out all the way to here, or maybe here, oops, right there, aligned with this. Now this is, let's say, your final data set, final point in this case, and you observed at least 12%. Let's say you wanted to measure 10, but you got 12, and you met the sample size requirements and everything, and it looks good. This mean of treatment is on the right hand side of this line, right? This is your threshold for control, and you got it on this side, which means it is also statistically significant, because when you now put Fisher's hat for p-value rejection, right? This event is so rare that but you have observed it, which means your model about null hypothesis for this readout is false. So you reject the null hypothesis. Now, what is the power of this experiment in mathematical terms, or in calculus terms? Whatever is the area for treatment bucket under on the right hand side of this threshold. So for example, all of this, right, it's the power of the experiment, of this experiment. And this is basically gonna be the power. It may or may not be your design power, which you wanted to be at 80% when you began. It may be close to that, maybe 75, 78, or whatever percent, right? But the farther this goes, the more separated these two normal distributions curve would be. And this is, in mathematical terms, the post hoc power. We don't worry about post hoc power most of the times. We just worry about our decisioning boundaries that we had made before we started the test, and not measure anything after the test, at least when we put the Neyman Pearson hat. So, or hypothesis testing. So all it matters in that case is, are you farther out from this alpha, and did you meet your sample size requirements? These two conditions should satisfy, and you can declare your treatment as as a winner. So you reject null hypothesis and you take your alternate hypothesis and you launch it. Now, but so what is type 2 error and why is it so significant? Um, so type 2 error again is the beta term, and normally beta is equal to 0.2 or 20%, right? Sorry for the handwriting, but this is 0.2, and power is uh, 1 minus beta, right? So power is equal to 0.8 when we do. And type 1 error, type 2 error is committing this error. So basically failure to reject this. For example, there was an effect, which means there was an effect over here, but you failed to measure that, maybe because you did not collect enough samples, or maybe you were measuring things that were too small and it was too hard to detect. So you failed to reject, even though there was, or you failed to launch it, basically, even though there was an effect. Now, depending on the business context, this can actually change dramatically. For example, um, in the context of medical, right? Let's say cancer example. Failure to detect a cancer when there is a tumor is fatal, right? The patient may not get to uh, go through treatment, and it can be fatal for the patient. So we want to minimize false negatives in that case. Another example could be in self-driving cars. You want to avoid the cars hitting any kind of barriers. So failure to detect a barrier when there is a barrier, it's gonna be a fatal again, or serious injuries. But on the other hand, if type 1 error for that same example, right? If there was no barrier, but you detected a barrier over there, um, you may take some action, but it's not gonna be a fatal. Maybe it could end up being fatal, where someone rear-ends you, but that is a possibility. But that is how it's interpreted. And in cancer terms, probably you don't have cancer, but it detected you have cancer. They may put you on um, bad therapy session without double checking. So that can again be a serious issue. So depending on the business context, these boundaries need to be controlled very well. So that's about the boundary, and that is what the type 2 error example that I gave you. You can use it if someone asks you, but it depends on context, when it could be fatal, when could it be serious. Let's quickly move on to the central limit theorem now. I hope this made sense. It is definitely confusing where two different theories are combined together and leads to confusion. But hope you can look into your data sets and kind of figure out which one works better for you. And I have some action plans for you available at the end. But let's quickly look at central limit theorem. Um, so central limit theorem, right? What does it say? Central limit theorem states that if you have a population with mean and standard deviation, blah blah, you take sufficiently large samples from the population with replacement, then the distribution of the sample means will be approximately normally distributed. What does this all mean, right? And why is it even important? So first of all, let's do this. What it's saying. Let's look at this, and let's do this with the same Hawaii rainfall data set. So what I'm gonna do is I'm gonna draw randomly like 5 samples from this. And what it's saying is if you take sufficiently large number of samples, right, then the means of these samples should be approximately normally distributed. So let me actually visually show you what it means. So first of all, let's take um, sample one. So actually, let's do this way. So samples or iterations, let's say iterations, and then we have let's draw 5. So draw one, draw 2, and then we draw 5 such samples, right? And then let's say I iterate 1,000 times. So I'll just extend this all the way down. Oops. All right, so there is a function to do this shortcut, but this is faster for me right now. Oops. What is happening? So we have 1,000 samples and we'll randomly draw. So first figure out ran between, and my lowest year is 1920 and my highest year is 2012. So this is not exactly the right way to do this, but this is the best I can demo you right now. Let's fix our readouts. So I'm gonna paste. So what I did is now, and then values. I'll put the values 1, values 2, and then we draw the values, right? So what it's doing is it gave me random 5 years. Now I'm just gonna we look these values up from here, and then so yeah, so I got these, and then I have these. So I drew basically 1,000 random samples. So basically I created 1,000 random samples, and I subsampled 5 of each, right? Now we take average. So that is what it says. You take the sample means, distribution of the sample means. So first we have to create the sample mean, so which is just the average of these 5 values. Now we have this, all right, and we'll plot this. That's the simplest thing that we can do. So here we got a very nice looking normally distributed chart. So this is the central limit theorem in action, in a nutshell, which means if you resampled data from your existing sample, all the averages of each of those samples will nicely form a normal distribution curve, which will be normally distributed. All right, so that's that. And why is this important though? Like, why does it even matter? So this understanding of the world helps us go inside out from here. So for example, I have this distribution, right? I know that a lot of natural processes will appear to be like this. So now I go inside out from here. So if I were to believe the central limit theorem, and if my average of this data point is somewhere around 68, right? Then this data set that I have, the overall 93 records that I have, it's not normally distributed, but it comes from a distribution. So let's say if I went back in years, right? If I went back a few million years, and if I had the data for each of those years, maybe that will form a nice distribution. So that is the population. This is just the sample that I drew from that population for last few years, right? So maybe that population would be normally distributed, but this is a representative of that sample in the case where right now it's looking slightly right skewed. It's not exactly normally distributed, but it's very small right skew. However, it does come from a population which is normally distributed. So having this understanding of central limit theorem helps us to make assumptions about our population from the sample that we draw, right? Um, and yeah, so basically we can say that, okay, this one is mean is same. So central limit theorem say the mean of the population is same as the sample mean. So we can say the mean of population is the same, and which is 68 something, and then the standard deviation is basically can be estimated to be the standard deviation of the sample divided by the um, the number of samples or subsamples that you took. So just to quickly show you, right, the standard deviation of this is 5.75. The standard deviation of this data set, right, this sample that we drew is going to be very different. It's 13, but we can estimate that the population standard deviation is going to be the sample standard deviation divided by square root uh, of the sample size. In our case, we drew 5 samples individually, so it's going to be divided by square root of 5, so it's about 6. So it's not that far away. It's about, it was 5.75, it is 6. This helps us estimate the 2 sigma level of the overall population, right? So 2 sigma is nothing but our p value or alpha threshold level almost. So if we just say the average of the population is this, then our sample is this, then our 2 sigma is this plus 2 times of that, which means if we observe anything beyond 80, it's going to be rare event, is what it says, 80.68, which is if we observe anything over 80, it is going to be less. Now, there is another concept that I want to now add in this mix. When I was demoing you these two curves, as we get more and more data, the curves don't remain in the same shape. They actually start getting narrower and narrower. So this boundary that I have over here, it's actually a moving target as you are collecting more and more data. So this is one of the biggest mistakes that folks make, is if you don't have enough samples and you make a decision beforehand, if you did not do your power calculation, this may end up this is a moving target, and in a given time frame you might get caught in a bad moment where it tells you p-value is static when in reality it might not have been. So I'll show you what I mean by moving target. I did the um, comparison for this. So I did the same CLT calculation, which is the central limit theorem, but I did 2 more subsamples offline, and I kept ready for you to show. Where in this example, the 2 standard deviation is 80, right? And this chart, let's just adjust this axis, right? So minimum is 50 and then maximum is 90. Oh, it's already adjusted. Perfect. So if I were to compare this chart, right? Let me quickly take a screen grab of this. This is at 5 subsample, like 5 subsamples, and I have one at 10 and one at 30. So as I increase the number of samples, the the shape of the chart keeps shrinking, like the normal distribution keeps getting narrower and narrower. You see, the first one is just 5 samples. It's so broad, it's so spread out, and it's short. As I go to 10, I see it has shortened. Like my 2 sigma level is now at 77. In the previous case, it was at 80 something, right? So it was far out. As I keep collecting more and more data, this shrinks and shrinks and shrinks. Eventually, it becomes so narrow that the 2 sigma limit is not far out from the mean, too much. So if you want to detect small lifts or small effects, you will have to collect lots and lots of data, because this distribution keeps shrinking and shrinking and shrinking, and you will get your 2 sigma levels pretty close to the mean. But you have to be cautious about this, because if you throw enough samples at any experiment, you will eventually get what you want out of it. So you have to, that is why you have to first decide your size, or you have to first do your power calculation, which is first estimate your sample size and then go from there and do this exercise. I don't know if this all made sense so far, but this is basically what happens under the hood of an A/B test data collection in a frequentist setting. It's obviously going to be very different when you use Bayesian or anything else in the mix, but this is what it is. For frequentist, and a lot of platforms use this, honestly, or even offline analysis are using frequentist statistics, t-test or z-test. So this is why it is very important. Even if the company has Bayesian, you will be interviewed on these concepts anyway. So as long as you understand this engine of statistics, how it's working as you keep collecting more and more data, you can associate it back to the p-value and hypothesis testing and their assumptions, and then come up with a better guiding decisions. I want to quickly show you this true positive calculator. Let's say you start with, and in terms of Neyman Pearson's thinking, what they are saying. So let's say you start with 1,000 hypothesis tests. You run 1,000 hypothesis tests over the year, and you have two paths. One is you have a theoretical win rate, right? This is not the win rate that you actually ship your experiments out to. This is your win rates of basically what might be in theory. But for simplicity cases, assume this is your actual win rate, right? What you launch. So let's say it's only 10%. So you test about 10 ideas, only one of them looks promising, and you launch it, right? So out of those 1,000, when you put 10%, you get 100 winners over the year. Now these 100 winners, you launched it. So now that becomes that is subjected to the power calculation, which is meeting the 80% power requirement. And the remaining 900 was your loss rate. You rejected your null hypothesis, right? And sorry, you failed to reject your null hypothesis. So this is your nulls, and on that you subject them to 5% alpha. So your true, so basically your false positive rate is 45 out of this. So basically 1,000 came to 900, and then 5% of 900 is 45, and these are the remaining true negative that you detected. And in here you launched about 100 of them, out of which 80 of them actually meets power requirements. So that is your true positive, and you compute your actual percentage of winners that you launched, or true positive rate. So true positive rate, by keeping these thresholds of alpha 5 and beta 20%, you reach actually 64. So in reality, you might only launch 64% true positives, right? But but you might be like, okay, this is not making sense, because I actually launch about 30% of my experiments, and that is how you can see, when you enter 30%, everything changes, and now you are at 87% true positive. This is true when, so for this, I want you to look at the another concept of law of diminishing returns, right? So when you have a new product or new company or new marketing campaign, like you're starting out the marketing campaigns for the first time, you will be in this phase where you will find a lot of easy wins, like low hanging fruit, and you have like a lots of winner experiments, and you will keep launching. So in the beginning you will have significantly high true positive rate, which is great. But as you come to a point of optimization, right, you will hit this point of diminishing returns, after which it will be hard for you to move anything on the metric. So at that time you have to assume that a lot of your ideas are just not going to move the needle. You will have lots and lots more ideas that fail to produce any real events, and you will have to adjust your win rates. And at that point it is absolutely important to adjust your alpha and beta levels. If you adjust your beta levels, it's not going to be too much. Let's say you change it to, you make it more strict, like now you want to observe 90% power. You're not going to change it too much. It's just hardly barely changes anything. What is the most important one is your alpha thresholds. When you make it more stricter, your boundaries of falsely rejecting null hypothesis reduces. um, so as a result, let's say you change it to 2%, right? Or yeah, 2%. So anything, now your p-value is the p-value threshold in real sense. When you combine these two theories, alpha does not mean p-value equals that, but let's say now you think that your p-value is 0.02, you have again increased your true positive rate significantly. So this is something that you have to keep in mind, and this, you can only tell your theoretical win rates by doing an audit of your experiments, like your past experiments, what you've launched and what you've actually been able to um, find true winners, right? And then adjust accordingly. If you look hard enough, you will find a lot of winners, but those may not be true. So you have to be careful about your decisioning boundaries over long run, as well as how you use or misuse p-values. So this is going to be an important tool if you have to um, if you have to kind of adjust your overall win rate in the long run, for especially for companies that have third party, like they are, you have an experimentation platforms, you integrate into other companies websites. This is not 10,000, it's not 1,000, it's like tens of thousands now. So this becomes even more important, where you overall win rates or true positive rates remains higher. But yeah, it still depends on individual companies to companies, because the decision makers are across the companies and they don't talk to each other, so there is no interaction effect that way. So yeah, this is in a nutshell. I wanted to cover everything about these topics. So yeah, I'll just mark all of these as gray. I covered the central limit theorem. Yeah, the action plan for you is basically what I went through, which is you go back to your experiments, and I'll just put everything together now. So you go back to your experiments, or you go back to your metrics, you dig into your data, you find out the distribution, right? You identify your 2 sigma levels for it, and then you form your alternate hypothesis, like okay, I want to meet at least in this case I want to observe at least 80.6% inches of rain, or 80.6 inch of rain. um, in your case, your 2 sigma would be in terms of lift value for that metric, whatever that is. So and you bound it. Of course, you can get these values differently depending on how much samples you throw at it. I covered that from the central limit theorem. The more sample you have, you can measure smaller and smaller stuff. So if it makes sense for your business to measure small things, do that. If it doesn't make sense for a company to measure small things, for example, if it doesn't make sense to improve a conversion rate by 1% when the return on investment is gonna be pretty much like maybe even like $200, you don't care for $200. You want ideas that will give you $200,000 or $2 million, right? So you translate these into your win percentage, like your minimum detectable effect or the effect size. Give it to your and data scientists and product managers work with each other generally to to come up with these thresholds, and then product managers can look back into their idea pipeline and see which ones of these have potential to hit such lift values, right? You don't want to just randomly test everything that's on the idea pipeline. It's not going to be best use of your time and resources. You want to strategically pick out the examples, or learn something from the past that gives you good estimates of how much lift you're going to get, and then use those to prioritize your experiments and run those experiments in the production. You would get wins faster. You would also use statistics better. Even though these two theories are combined, it should confuse you less, hopefully, going forward from this after this lecture. And maybe it helps you run lot more better and higher ROI experiments. Um, there are advanced techniques in statistics which gives you now even better tooling to do this. But again, some of them still have the same argument, because if you don't understand why those are better than this, or if you don't understand what are the shortcomings of this, there is no point in just going to the shiny thing just because it's out there. You have to understand what works for your data. And in most cases, frequentist works fine. It's just companies who have over optimized already their whole process. That is when the need for going to better methods is more important. So that is all that I wanted to cover in this session. Yeah, so hopefully I went quite a bit over. So hopefully this was a good session for you. Sorry, I'm not going to be having time to take questions. I will also have the uh, yeah. So all the advanced topics that folks have been asking on the thread, like I see someone asking multiple comparisons problems and things like that. It's all of those are advanced topics I don't want to cover right now. I hope there was a good argument in the chat. I'm seeing a lot of comments. I will go through them offline and see what are the questions that folks have been asking. And yeah, meanwhile, I've not been able to read your questions or comments here. So I would encourage you to send me a connection on LinkedIn. I'm open to chat, and please, please, please tell me how I did it, um, whether it was worth your time, whether I added any value to it, whether it cleared any of your concepts in how the statistics engine or the basic frequentist statistics work in in the uh, in the backend. So I was able to hopefully visualize that and simplify that for you, and hope you have a better understanding of what p-value is, under what circumstances it was created, and what hypothesis testing is, and under what circumstances that was created, and how these two things will never align in your readouts, because your sample size requirements may be 100,000 samples to measure 5% lift, but your experiment readout says you have 70,000 samples, you have 7% lift, slightly higher than what you wanted, but the p-value is already stat sig. Now it's up to you to make a decision. If you wear Fisher's hat and you were to decide a winner, you would say p-value is less than stat sig, let's just launch it. If you had to decide on Neiman Pearson, if you had to wear based their hat and decide, should I launch it right away? Maybe you want to wait until you have 100,000 samples and wait and see whether the 7% lift holds true, or if it drops down after 30,000 more samples come in, right? It could be that it might change. You never know. So in the long run, it will help you do better. But in that specific experiment, you might have to reject it, even if there was an effect available. So these are the two pros and cons, and you have to use these tools wisely and correctly. And yeah, so yeah, send me a message, drop me a note on LinkedIn, send me direct message, tell me whether I was able to explain the topic well. Was it worth your time? I am open to feedback. If I don't take feedback, I would not know whether I am either good at this at all or not. How can I change? Should I enhance some of my examples? So on and so forth. If I hosted another session, would you attend? Um, and yeah, if you have any other kind of questions on career data science, you want to collaborate on anything, just drop me a message. I am looking forward to talking to you, a lot of you. And yeah, thank you for your time again. And I will share the recording in private. Just reach out to me, and I will send you the link for the recording. Because of the technical issues, it was a lot of problems that I see that folks have been encountering. So yeah, all the questions just send me back on the LinkedIn. I'll still go through this, and I will respond to as many people as possible um, directly on LinkedIn. But yeah, obviously reach out to me. All right, thank you so much, and you have a great rest of your day, and yeah, good night for people on the other end of the world. Thank you so much again. Bye.